Welcome to my Fractal Topology of Spacetime theory. My name is Bob Howard and this is my interpretation of how the universe works. In this, the first part, I show how I developed this theory from a possible explanation that I had for the phenomenon of dark flow. Although entitled dark flow, this first part is more about my concept of how and why the universe expands.
After watching the BBC's Horizon programme, Is Everything We Know About the Universe Wrong?, where Sasha Kashlinsky introduces the latest phenomenon in cosmology, dark flow, I began to realise that I could offer a tangible explanation for this phenomenon. If what I was thinking was right, then a lot of current thinking must be wrong. It led me to think about the universe in a totally different way, and I have now found a way forwards to explain how the universe works in a cyclical, a more eternal way, without the need for dark matter and dark energy, and even why the Big Bang happens. But let us not get too carried away, for the explanations here only satisfy my curiosity as an amateur self-taught scientist. Nevertheless, I am pleased with my achievements, even if they turn out later to be wrong. As our observing instruments improve, we are able to see ever further into the cosmos. Hubble deep field images have now revealed galaxies so far away that the look-back time is within 3% of what our current theories predict the age of the universe to be. Looking at an area of about 1/10 of the size of the Moon, this image reveals 6 new galaxies and 1 reclassification. When we look at the properties of the earliest galaxies, they appear to be surprisingly mature, for they already contain a reasonable amount of heavier elements from previous generation stars. In other words, we are still not seeing the first evolutionary step in star formation, the population 3 stars. This galaxy was first given a redshift value of Z10 in 2011, has now been reclassified at Z11.9. Dark flow is the name given to an apparent movement of galaxies seen with the aid of gravitational lensing and new analyzing techniques. Comparing images over time, it would appear that these galaxies are tending to move closer together and are disappearing from detection, indicating an incredible peculiar velocity towards the cosmic microwave background. When we look at the data more closely and apply corrections to fit our current theories, this peculiar velocity becomes, well, less dramatic. Current theories, though, require that we make up 95.1% of the universe. So I thought I would interpret for myself what could cause the effect. Many have difficulty with the concept of an expanding universe, and one analogous way often used to describe this expansion is to place buttons on an expanding balloon. The buttons symbolize galaxies, and like galaxies they stay the same size during the expansion. The curvature of the balloon is a little misleading, for the expansion is more homogeneously three-dimensional, like the currents in this rising fruit loaf. Although we have a homogeneous movement of the buttons during inflation, this diagram has a stationary position at the point of inflation, and so we can imagine that to be our position. And so when we look at the movement of the closest and furthest buttons, and compare the way they move during the expansion, we see the furthest recedes away faster. It has a faster recessional velocity relative to us, the observer. Imagine this line travelling at the speed of light across a galaxy like our own Milky Way. It would take about 100,000 years to get from one side to the other. Imagine now that it is a flash of light from Betelgeuse going supernova. It would race away from us at the speed of light, but as space stretches in the future, that light travelling through the stretching space will speed up relative to our position, but it does not exceed the speed of light in any frame of reference. That light in the future will have a velocity relative to the source greater than the speed of light. If we use light to measure distances, future distances then are relatively shorter than past distances. This time the arrow remains at the speed of light relative to the observer. What this now indicates is the differential between the recessional velocity of the galaxies and their local space relative to the constant speed of light over increasing distances from the observer. The recessional velocity of the galaxies that it now crosses are receding ever faster with distance. At x, this recession is equal to the speed of light. From then on, the space and the galaxies it contains are receding faster than light relative to the observer. X marks the interface between luminal and superluminal recession, and we call this the Hubble sphere. To an observer, indicated here by the red circle, all distant galaxies are receding away. The further away from the observer, the greater the recessional velocity. This linear relationship between distance and velocity is known as the Hubble constant. The average increase in velocity is calculated to be 67.15 kilometers per second per megaparsec. At a far enough distance, the recessional velocity will become equal to the speed of light. This interface between luminal and superluminal recession is known as the Hubble sphere. In a universe that has always been accelerating, galaxies will be crossing this interface. The Hubble sphere is not a special place. It is just a distance relative to the observer. If we move the observer to a different galaxy, we move the Hubble sphere. As the galaxies recede away from the observer, they cross the Hubble sphere. The colour change in the left of this diagram represents this interface. A photon from a distant galaxy will take longer to reach an observer than one from a closer galaxy, but we also have to consider that the distant galaxies are moving away faster. This time, 2 photons are emitted at half-second intervals to indicate an event. We can see that an identical event from the receding galaxy B will appear to take longer to the observer. In this image, we see a galaxy receding past the Hubble sphere. Any photons that leave the galaxy after it has passed the Hubble sphere will never be seen by the observer as it is carried along by superluminal space. These photons will then start to travel backwards, but only relative to us, the very distant observer. The more distant the galaxy, the older the light, the longer the events appear to take. Time will appear to stand still when a galaxy reaches the Hubble sphere. Now you may think that the galaxy will disappear as it passes the Hubble sphere, with no future light being able to outrun the receding space. But you would be wrong. The cosmic microwave background radiation is light from way beyond the Hubble sphere, and we can detect this. We will still see the galaxy, but instead of aging slower, it will appear to get younger as we receive the photons in reverse time order. A similar thing can be heard with sound here on Earth. If shot at with a high velocity rifle, we hear the bullet before we hear the gun fire. The sound from a modern tank firing from 5 miles away will take longer to cover the distance than the high velocity shell. And in this example, an observer at X will hear the events in a different order than what is seen. The numbers indicate the sound of the shell going through the air produced 1, 2, 3, 4, 5, and heard at X as 5, 4, 3, 2, 1. The first thing we see is the tank fire. The shell is then in the air for about a second or more, and the target is hit. The first sound will be the target blowing up. Then we hear the shell travelling through the air for a full 24 seconds before we hear the tank fire last of all. In 1675, the Danish astronomer Ole Rømer first estimated that light had a finite velocity with astronomical observations of Jupiter and one of her moons, Io, that are of interest to us here. Observing the transit of Io, he noticed that the ellipse times were earlier when Earth was closer to Jupiter at opposition, and then later at conjunction when the Earth was furthest away. The delay time at conjunction was due to light taking a finite time to travel the greater distance. Ole Rømer was using Io's orbit like a giant celestial clock. If we were to consider the celestial clock as being correct at opposition, then at conjunction it would be 22 minutes slow. Whilst travelling from conjunction, we would see that Io's orbit would gradually appear to speed up. So when the celestial clock would be correct again at opposition. As Earth travels away from Jupiter, it will appear to slow down. If we now consider we were in a spacecraft and were to keep on travelling away from Jupiter, as the look-back time increases with distance, Io's orbit would appear to keep on slowing down ever slower. And this, in effect, is what is happening when we look at distant galaxies as their recessional velocity increases with distance. Just like when the transit of Io slows down, when we were moving away from Jupiter, the rotation of a galaxy will appear to slow down with ever-increasing recessional velocities. Imagine that we were looking at this galaxy as it approaches our Hubble sphere. It will slow to a standstill when it reaches the Hubble sphere, and then, as it goes beyond the Hubble sphere, it will appear to rotate in the opposite direction. So any movement beyond the Hubble sphere will appear to be occurring in reverse time order, just like a film being played backwards, with the events appearing to speed up in reverse the closer the objects are to our visible horizon. If we were to study merging galaxies beyond the Hubble sphere, they would appear to be separating. If we could look back far enough, where the reverse time order effect is much faster, we may even see it happening. So way beyond the Hubble sphere, as recessional velocities continued to increase along with the look-back time, the reverse time order effect will speed up and eventually go exponential at the Big Bang moment. You can see that this simple notion of delayed look-back time can account for the way we perceive changing expansion rates in the past. The visible objects with fastest recessional velocities are not the Hubble ultra deep field images. The earliest visible objects are the first atoms, what we are looking at when we observe the cosmic microwave background radiation, and they are receding so fast relative to our position in time and space that their light emissions have been redshifted to Z 1000. There seems to be a great disparity between the redshift of the furthest galaxy detected so far at Z12 and the cosmic microwave background at Z 1000. There is one way to reconcile these differences, and that is to consider the components of time and distance as variable. If future distances are shorter and future time slower, then past distances are longer and past time relatively faster. With the Hubble telescope, we discovered far more galaxies than we had ever previously predicted. That, though, is nothing compared to what I am suggesting here. With a steady expansion rate throughout the history of our universe as a function of time, then Z1000 is a very far and ancient place indeed. A large area containing a lot of mass, like a large galaxy or galaxy cluster, can distort the surrounding space, making a kind of celestial magnifying glass, distorting the older light from behind it. This gravitational lensing effect can be used by astronomers to see ever further into the past. Although it can give multiple images or Einstein rings, these distortions can be corrected with a resulting image that can have up to 50 times magnification. The gravitational lensing effect and very fast recessional velocity may be the cause of the apparent movements associated with dark flow, and the galaxies disappear as they go beyond the sensitivity range of our imaging cameras. We know that in the future we will see fewer galaxies as the universe expands. You may wonder how these galaxies will disappear from our view. The thing is, our universe is infinite, and I believe it must be. Then galaxies have been disappearing in our past. They must be disappearing right now, because look-back time past the Hubble sphere is in reverse time order. As the Hubble flow moves the galaxies towards the cosmic microwave background, they get progressively younger. If we are ever able to see the very first stars, they will appear to be, going out as they become younger. The galaxies that contain them will have a quasar in the middle, and that too will go out as the galaxies revert to the nascent pristine clouds that then heat up and reverse morph into the very first atoms and become the cosmic microwave background. I believe dark flow is a precursor to this effect. The cosmic microwave background is where the nascent clouds of pristine gas recombine to form the infinite plasma cloud that was the beginning of matter in our aeon of time. You may think of it as a surface, but it is a different surface moment by moment. Our hunt for the elusive dark energy that is said to be actually pushing the universe apart will, I believe, be as fruitless as an attempt to find the treasure at the end of the rainbow. If the recessional velocity of distant galaxies is due to stretching of space and not a real movement through space, then why do we need real energy to make them move? Time may be a consequence of energy, but no energy is lost to produce time. Thank you for listening. I hope you will continue to follow me down the rabbit hole of that ever-deepening fractal depth of the fractal topology of spacetime. It is a very different story to that of the standard model, and who knows, much of it might even be true.